I apologize for the delay of this video. I've been swamped with other little projects in my class. Okay, so this video is in reference to Orifice flow meter. So it isn't a difficult one. It's a pretty easy lab. So what you actually did was take pressure readings and volumetric flow rate, and I'll show you in a minute exactly what you're going to do. So first of all, let's talk about what exactly is a flow meter. Well, a flow meter is a device that measures volumetric flow rate based on the pressure. There's three types of metering devices that can measure volumetric flow rate based out of pressure differential. The first one and most inexpensive one is called the Orifice flow meter. It's basically a pipe, and then there's a plate in between. There you go. So Orifice flow meter. The second one is known as a flow nozzle. So that one has a little bit of a curve. There you go. Flow nozzle. And the last one is known as Venturi. Very smooth. And basically what this does, it measures pressure differential. Let us suppose that the fluid is traveling from right to left. So this will be pressure 1, and over here will be pressure 2. Same thing over here, pressure 1, and over here will be pressure 2, and this over here will be pressure 1 and pressure 2. Venturi. So basically this pressure differential, there's a set of equations so we can do, and it will give you Q, the volumetric flow rate, or for an incompressible fluid, mass flow rate. And that's exactly what we're going to be looking at. When I came up with this problem, it was when the original Orifice flow meter experiment was not working correctly. So I actually bumped into this guy right here, which is example problem 8.12 in Fox. So, and this, it was just exactly what I was looking for. It gives you the volumetric flow rate, Q. It gives you the diameter of the pipe, right here. It does not give you the opening of the orifice plate, and it also gives you the pressure differential. So, and that's exactly what you guys have. You guys have a 1-inch pipe. In reality, yours is 0.987 inches. That's the ID. You also have Q. So, so basically your D1, your diameter, is known. You have Q, and that's in, you guys have it in cubic inches per second, right? And then you also have delta P. Obviously, you guys have it in inches of H2O, which you need to convert to pascals or PSF in order for you to make sense of some things. So I'm going to put in red, you have this, and you have that. This is, again, this is your delta P. And what you're going to be looking for is for dt. And dt is basically the diameter of the opening of that plate. So we're basically going to be following the procedure here in which we have to find dt. But a lot of students, even though I print this out and I give them to them, they don't make much sense of it. I posted this online, I believe, but I would like to take a little bit of time and explain what's happening here. First of all, in this particular problem, the fluid that's being used, it's, let's see, I believe it's air for this one. For our, yes, it is air. For ours is water. So this is the governing equation right here that pretty much sets what our mass flow rate is, and if you know the density, what our volumetric flow rate is. And it is based out of several components here. K, which is known as the flow constant. AT, which is actually the area of the opening, which is right here. So D, from there you can find AT. AT is equal to, remember, if you have the diameter, it's pi over 4 dt squared. So, and then of course the density of the fluid that you're working with right here, and the change in pressure. So this is basically things that you can get. This is your only unknown. And you could say, well, I don't know K either. So what we can do is manipulate this equation a little bit more so that we can utilize figure 8.20, which I'll pop up in a minute, and for us to solve the unknown dt, that since that one's the one that we don't know. So what they do here, they do a little series of manipulations of area and beta, but they don't really explain what those things are, and that's what I'm here to do. I'm here to explain those things. So I'm going to open up figure 8.20. I have that over here. Let's see, figure 8.20. Here we go. And this is only for the orifice flow meter. Okay, that's something that we need to make aware of. Only for the flow meter. Orifice flow meter. In other words, this figure 8.20 right here, it's only for orifice flow meter. Flow nozzle gets its own graph, and Venturi gets its own graph. As you can see, on the x-axis, we have Reynolds number, rho VD over mu. And of course, we have beta. What the heck is beta? Beta is a ratio between the orifice opening diameter and the pipe diameter. So obviously it's always going to be less than 1, because how can the opening be bigger than the pipe, right? So it's going to be a fraction. And these lines right here pretty much represent the flow coefficient depending on the Reynolds number. So you have the diameter beta, diameter ratio beta, and then you have the Reynolds number, and on the right side we have the K, which is a flow coefficient, which is necessary for us to find out our dt. So let me go back to this one right here, and let me just manipulate this equation the same way they did, the following way. We know A1. Why? Because we know D1. A1 equals 2 pi over 4 D1 squared, in which we already know the diameter of the pipe. I just gave it to you earlier. Now remember that beta equals to dt over d1. So we can actually write this the following way. What they do here is they give you beta squared. Well, why did they do that? Because area is d squared. So check out what happens here. If I do beta squared, this is equal to dt squared over d1 squared. But remember that if we have a1 and then at, I'm sorry, and then we divide that by a1, check this out. At is pi over 4 dt squared, and a1 is pi over 4 d1 squared. So pi over 4 and pi over 4 is basically a 1. And we end up with dt squared over d1 squared. This is basically beta squared. Look at that. So basically beta squared takes the place of at divided by a1. So why did we do that? The reason for that is because when we put beta squared, right, and we multiply beta squared times a1, what does this equal to? Well, a1 times a1 cancel, and this is basically at, which is an unknown. If we find at, we can find our dt, which is our ultimate goal. So that's exactly what they do. They get beta squared times a1 right here in substitution of at. Now let me continue telling you what they do. So they pretty much know that the mass flow rate, which you have, and you're like, what do you mean we have it? This is basically your Q multiplied times density, and that's your mass flow rate. This mass flow rate is equal to K beta square times A1, and this is multiplied times the square root of 2 rho delta P. So I'm going to put in green the things that you know and have already. You have this, you have this, you have this, and you have that. So you can treat this as a K beta square is equal to some type of constant. If you divide this by A1 square root of 2 rho delta P, and over here A1 square root of 2 rho delta P, you end up with this right here. And that's exactly what they do over here. They have K beta squared being equal to some constant. And then what they do, they say, or K is equal to that constant divided by beta squared. It doesn't matter which one you use. So what do they do next? They do what is called iterations, guys. Iterations. In other words, they try something, they plug it into the equation, it didn't work, they just try something else. Yeah, I'm getting closer, and they keep going and going and going and doing iterations. So the very first thing that they do in this problem right here, which again you can use as a reference, but I'm just explaining to you. The very first thing you need to find out is the Reynolds number. That's rho VD over mu. And these are quantities that can be found in the back of your book for water, for your case. In this case, because the fluid is air, they found it for air. They found out for this particular problem that the Reynolds number is 3.49 times 10 to the fifth, which is about 3.5 times 10 to the fifth. And then they go back to this one right here. 3.5 times 10, this is 10 to the fifth, 1 times 10 to the fifth. And 3.5, it's roughly around this area right here. Okay, so I'm going to use orange, and I'm going to make a line. Oops. A perfectly vertical line. That's good enough. There you go. And then I'm going to make my very first guess. So I'm going to guess that beta is equal to 0.75. In other words, it's going to lie somewhere in here. Well, then I make a horizontal line where these both intersect, and basically what I do, I get my very first K. I make it nice and horizontal. There you go. Boom. So my very first K value, of course me guessing that beta is 0.75, is basically this right here, which is about a 0.7222, I guess, 21. Let's see what they did. they did their very first guess. Yeah, 0.72. They guessed that beta was 0.75. And all they have to do now is plug it back into this equation over here, which is what they have right here, and see if it makes sense. So they have the very top number is 0.295. That was their constant. Our constant is going to be different. They divide by beta squared, and then they say, what's the k based on this? Well, our k is 0.524, but wait a minute. Our k is not that. Our k on this is 0.72, so no, we're way off. So then they take another guess, and then they guess this point right here, that beta is 0.7, and then 0.6, and so on and so forth. So they take what it's called iterations, and then basically out of those iterations, they're getting closer and closer and closer. K should be 0.69, they get 0.62. And then when they do the next iteration, K should be 0.67, we get 0.69. And basically they trim it down until finally they get the beta should be approximately 0.66. And basically this equation now starts to make sense. Okay? And then once they find their beta, well, remember that beta equals to dt divided by d1. You already know this one. You just iterated beta, and this is your only unknown, and that's how they're able to get dt. So you have 3 delta p's with 3 q's. So you're going to do this 3 times. And you're going to get a dt for your first one, a dt for your second one, and a dt for your third one. Now, you could say, sir, I got very different dt's, or my answers doesn't make sense. And what that means is basically that the volumetric flow rate that you have is basically outside the working range of that orifice flow meter. Because these are the advantages and disadvantages of using these. An orifice flow meter has very high delta P, which can be bad because you only have a specific zone or a specific range of volumetric flow rates in which this device is accurate. The cost is very low. And I think you can see this in Fox also. So this is medium delta P, and this is medium cost. And this is very low delta P, but very high cost to produce. High cost. So this is obviously what you want, except they're hard to make and they're very expensive. It has a much wider range for volumetric flow rate, but very accurate. This is very inexpensive. This is what we're currently using. However, it only has a limited range. Our very first experiment on the on orifice flow meter, it had three different pipes, which you probably read. One had a very small orifice opening, the other one had a medium size, and then the last one had a bigger size. And basically, this one only had a range of 0 to 1 gallon per minute. This one had a 1 to 3 gallon per minute, and this one had a 3 to 6 gallon per minute. If you go outside this range, the percent error was huge. If you were within that range, that working range, basically you were 90% accurate or above. If you take a look at figure 8.20, it pretty much tells you that if you're outside this range or outside this range, Reynolds number is too large or too small, your accuracy really it goes down. So I hope this video helps you understand those two attachments that I made on Blackboard. One of them, of course, being example problem 8.12 and all that they go through right here. Remember, they're using air. There's a density of air, and then they're using water right over here. because of the specific gravity. So luckily for us, everything is in um, the same fluid for us. It's water and it's inches of H2O. So my suggestion to you is from the very beginning, convert that pressure into pascals. And if you stay within the same unit system as SI, then your P should be in kilograms per meter cube, your area in meter square, your m dot actual should be in kilograms per second, and all of this should make sense. And then at the very end, you can convert from meters, because obviously your dt is going to be in meters. You can convert your dt to inches. um, I already have the answer in inches, and basically I can tell you if you're going to be within the ballpark. If two of these answers right here, if two of these are about the same and one of them's not, basically it means that these are closer to the working range. But I think, I'm almost positive that for yours, I need to double check, all three of them should be around the same ballpark. Plus or minus like 3/100ths of an inch, give or take, guys. So I hope this video helps. I apologize for the delay, and well, thank you very much.